Hello class, how you all are doing? I hope you all are doing good and you all are well. So welcome to the channel and welcome to the playlist in which we are discussing about uh, the transformations which helps us to transform my time domain signal into a frequency domain signal and vice versa. So up till now we have discussed about the Fourier series, and today we are going to discuss about the Fourier transform, and we also will try to cover most of the properties of Fourier transform. So in this lecture you will need good knowledge of calculus, so it will be good if you remember your calculus classes or if you revise the calculus. The second thing, that in the previous lecture we have discussed about the Fourier series, so if you want to check that out, please check it out on the I button. The link will be flashing on the top right hand side corner of your screen, so just click on it and you can check that video out. So now let's move further with Fourier transform and frequency spectrum of periodic signal. So first, what is a Fourier transform? So basically Fourier transform is a transform which allows you to uh, move your signal from time domain to a frequency domain. And how does it do it? So it can be done with the help of this formula you are seeing here. If my base signal is x of t, so you can give the Fourier transform of x of t is equals to, you can take the Fourier transform of x of t and you can get the signal, the frequency signal x of omega in output, right? So when you do the Fourier transform x of t, how will the x of omega look like, or the resultant output signal will look like? So x of omega will be equal to integration minus infinity to infinity x of t e raised to minus j omega t into dt. That is the formula for to convert my signal into Fourier signal. After that, except for this formula, uh, if you directly want to convert it into frequency, if you don't want to go for omega, which is basically 2 pi into f. So if you directly want to go to frequency f, you can do that too. You can take in x of f is equals to integration minus infinity to infinity x of t e raised to minus j 2 pi f t into dt. That will be value of your x of f. Okay, so um, even though I don't need to mention it, but I'm still mentioning it. Even though x of t is a time domain representation of my signal, and x of omega or x of m are frequency domain representation of my signal, right? And sometimes we write x of omega as x of j omega as well. Those who have worked in mathematics and complex number systems, they know this. And same ways we can also obtain time domain back uh, from this frequency domain by simply applying inverse Fourier transform. So the formula of this is also given here. You can same ways you took the integration of time domain, you can take the integration of frequency domain and you can get the time domain as an output. So the formula for x of t, uh, which basically is a conversion from frequency domain back to time domain, can be given as x of t is equals to 1 by 2 pi minus infinity to infinity x of omega e raised to j omega t into d omega. So initially we did the integration by taking dt as base, and then this time we will take the integration by taking d omega as base, right? D omega or df, whatever you want to take, you can take it as a base. So Fourier transform allows us to move from time domain signal to frequency domain, and vice versa. It also allows us to move from frequency domain to time domain. Now if you remember previous class, we discussed about the Dirichlet conditions for for one signal to be a Fourier series signal, there were some conditions, and following such conditions, your signal can become a Fourier series signal. So same conditions we are having for Fourier transform, and following those conditions, if those conditions get satisfied, then your function x of t will be uh, able to we will be able to find the Fourier transform of my signal x of t if those Dirichlet conditions satisfy. Now, as I've already mentioned, the four conditions in Fourier series as well, and the four conditions are same in Fourier transform as well. So I'm not mentioning all four of them here. So if you want to know about the Dirichlet conditions, please check out the last video. And all these conditions are sufficient, but not necessary for my signal to be a Fourier transformable signal. Okay, if either of the condition is not getting satisfied, still I can find the Fourier transform of my signal, right? They are sufficient, but they are not absolute necessity for my signal to be a Fourier transformable signal. Now let's see some of the Fourier transform properties. So I have already told you that there are so many properties for Fourier transform, so we will try to cover most of them. So let's initiate with the linearity property. So what does linearity property says? It says my Fourier transform of linear combination of signal will always be equal to the linear combination of my Fourier transforms, right? So basically you need to satisfy the superposition theorem, and if your signal can satisfy the superposition theorem, then your signal is a linear signal, right? So that's your linearity property. Mathematically you can express it by this formula: z of t is equals to if your z of t is equals to ax of t plus by of t, then the Fourier transform of z of t will be z of omega, right? So Fourier transform of that signal should be z of omega is equals to ax of omega plus by of omega. Now how? Let's try to check that out. So let's try to find the Fourier signal of this z of t. So what we will do, we will apply the formula for Fourier transform which we saw in the first slide. So what will happen, we will get minus infinity to infinity z of t e raised to minus j omega t into dt. Now you know what's the value of z of t. It is ax of t plus by of t. So what you will do, you will substitute the value of z of t here. So it will be equal to minus infinity to infinity ax of t plus by of t e raised to minus j omega t into dt. Now what you can do, you can take these constants a and b out of the integration, and you can multiply this e raised to minus j omega 2 inside the bracket. So what we will get, we will get a integration minus infinity to infinity x of t e raised to minus j omega t into dt plus b integration minus infinity to infinity y of t e raised to minus j omega t into dt. So again check here, the whole term except for a before this plus sign is actually the formula for Fourier transform. So it is formula for x of omega, and same ways after b, this whole term is the formula for Fourier transform of y. So uh, instead of this term we can write b into y omega. So we wrote that, and by doing that we are getting our output. So we just proved the linearity property here, right? So the second property is called time shifting, and time shifting is again same old property which we saw earlier in the previous chapters as well. So what does it say? So it says a shift of time t0 in my time domain will be equivalent to introducing a phase shift of minus omega t0, and amplitude will remain same as same as previous, right? So what is the mathematical expression for that? So mathematical expression for that can be given as y of t is equals to x t minus t0 if your signal is having the if your signal is represented by this formula which I've just stated. And if you are taking Fourier transform of that, so your Fourier transform will be y of omega is equals to e raised to minus j omega t0 x of omega t x of omega, sorry. So let's try to prove it again. So whenever we will take the Fourier transform of my y of t's value is equals to x of t minus t0. So here we are taking x of t minus t0 in integration, and we will have e raised to minus j omega t into dt as it is, right? Now what we will do, we will put t minus t0 instead of tau, and then we will take t is equals to tau plus t0 and we will substitute it. Remember when we were discussing associative and distributive properties for my system, we did almost similar thing. So we will do the same thing here. So what we will get y of omega is equals to minus infinity to infinity y of tau e raised to minus j omega t plus tau 0 into d tau, right? So instead of t minus t0, what did we did, instead of this t minus t0 we put tau, and instead of this t, what did we put tau minus tau plus t0, okay. And instead of dt we will get d tau, because whenever you take differentiation of this term, the dt will be equal to d tau, so we will put d tau, which of course will be equal to minus infinity to infinity y of tau e raised to minus j omega tau into e raised to minus j omega t0. So we simply separated both of the values, and then we have into d tau. And now if we take this e raised to minus j omega t0 outside of my integral, so what we will be left with, we will have minus infinity to infinity y of tau e raised to minus j omega tau into d tau. And again see, this is the formula of y of omega, this is the formula for Fourier transform of my y of tau, which is y of omega. So we will get e raised to minus j omega t0 y of omega. So here we proved the time shifting property as well. Same ways, as the time shifting, we are having frequency shift. And what does it says? It is same as time shift. So it says that by shifting the frequency by some angle, some beta in frequency domain, it will be equivalent to multiplying the time domain by signal, time domain signal by e raised to j beta t. Okay, so it is in a way you can say it is the complementary property to time shift, or the kind of reverse property of time shift. So it indicates that by shifting frequency by beta in frequency domain, you will get equivalent effect in as multiplying the time domain by e raised to j beta t. And you can mathematically express it by this formula, y, if your y of t is equals to e raised to j beta t into x of t, and when you take the Fourier transform of your signal, so it will be y of omega, and the Fourier transform of your signal will be x of omega minus beta. Now how will it be? So let's see how will it be. So here you are taking Fourier transform of your input signal y of t. So and the value of y of t is of course e raised to j beta t into x of t. So by taking a Fourier transform, we will get integration minus infinity to infinity my signal, which is e raised to j beta t into xt, into e raised to minus j omega t into dt. And after processing that, what we will get, by mean processing I mean simply we are taking the separated values which are having t common in them, j into t common in them. We will take whatever mathematical or arithmetic sum it comes, either if it is addition we will add it, if it is subtraction we will subtract it. So what we will get, e raised to minus j omega minus beta into t, okay. and rest of the terms will remain as it is. So final term will be minus infinity to infinity x of t e raised to minus j omega beta t into dt. Now when you see this, you will again realize this is nothing but the Fourier transform of x of uh, omega minus beta. So you will get x of omega minus beta as an output. Next property is time scaling property. So what happens is this property, it says the compression of a signal in a time domain is equivalent to the expansion in the frequency domain and vice versa, right? So you must have seen this time scaling property earlier as well when we were doing the numericals in the first chapter or second chapter. So we basically call it scaling property. We don't often call it time scaling, we call it scaling property because it works the same in both the domains, time as well as frequency. So we call it scaling, and it can mathematically represented as y of t is equals to ax y of t. If your signal is y of t is equals to x a of t, and when you take the Fourier transform, what will happen? Your Fourier transform will be 1 by modulus of a was the constant multiplied with your time. So you will get 1 by a x of omega divided by a, right? So that will be the Fourier transform of your uh, signal which is having some constant multiplied with its time. Now how will it be? So let's see, you are taking the Fourier transform of your signal again. So you will be getting minus infinite integration minus infinity to infinity x of a t e raised to minus j omega t into dt. Now again what you will do, instead of at you will use tau, and instead of t what you will do, you will get tau by a. So whenever you will take the differentiation of this term t is equals to tau by a, what you will get, you will get dt is equals to 1 by a into d tau, right? Because a is your constant. So you will get dt is equals to 1 by a into d tau, and the limits will remain same because we are not doing any big changes here. So uh, by doing this, what you will get, you will get this 1 by a ahead here. Let me change the slide. Okay, you will get this 1 by a in front here, and except for that you are mentioning at is equals to tau, so x of tau e raised to minus j omega, and I've also said that we will write t is equals to tau by a, so we will write tau by a, right? And when you take this 1 by a out of integral, you will be left with minus infinity to infinity x of tau e raised to minus j omega divided by a into tau into d tau. So again this is formula of x of omega by a, right? That's the Fourier transform. So by doing that we got our time scaling property. Now let's come to the frequency differentiation property. The frequency differentiation property states that the differentiation or differentiating by differentiating the frequency spectrum, it will be equivalent to multiplying the time domain signal by complex number minus jt. So how does it happens? So first let's see how it can be represented mathematically. So mathematically it can be represented as minus j2 x of t. This is your base signal minus j2 into x of t. When you take the Fourier transform of that, you will get d by d omega x of omega. And let's try to find the proof of that as well again. So we will take the input signal of ours in the integral minus infinity to infinity x of t into e raised to minus j omega t into dt. Now when you do the differentiation of your output x omega, because x omega is the formula for Fourier transform of x of t. So when you take differentiation of your x omega, what you will get? The equation will look like this: integration, here you can see minus infinity to infinity x of t d by d omega e raised to minus j omega t into dt. So what is the formula? What they are doing? What is the integration of e raised to what is the differentiation of e raised to minus j omega t? So it will be minus j omega t into e raised to minus j omega minus jt, minus jt into e raised to minus j omega t. So the whole term will be integration minus infinity to infinity x of t minus jt e raised to minus j omega t into dt. So by taking minus j omega t outside the integral, we will be left with minus infinity to infinity x of t e raised to minus j omega t into dt, which is basically the formula for the Fourier transform of x of t. So we will be left with minus jt into x of omega, and that defines your frequency differentiation property. So after frequency differentiation property, we are having the time differentiation property, which is quite similar to the frequency differentiation property. So what does it say? So it says the differentiation in time domain will correspond to multiplication by j into omega in the frequency domain, right? So what did frequency domain said? It said differentiation in the frequency spectrum will be equivalent to the multiplication in the time domain by minus jt. And time differentiation is saying that differentiation in time domain will correspond to the multiplication by j omega in my frequency domain, right? So it can mathematically expressed by d, if you are taking differentiation of your input signal x of t dxt by dt, and if you are taking Fourier transform of it, you will get j omega into x of omega. Now again, let's try to prove it. It's pretty simple. You are taking differentiation of your signal, which is getting a Fourier transform. So x of t will be equal to 1 by 2 pi integration minus infinity to infinity x of omega e raised to j omega t into d omega. So this is the formula for Fourier transform of your signal. Now what you will do, you will take differentiation of x of t. So dx of t by dt or dx by dt will look like 1 by 2 pi will remain as it is, minus infinity to infinity x of omega. Now what is the d by dt of e raised to j omega t into d omega? So you will get j into omega into e raised to j omega t, right? That is your differentiation of e raised to j omega t with respect to d omega, not dt. We are taking the in the Fourier transform Fourier domain, we are taking differentiation with respect to omega. So by taking this j omega out, what you will be left with? You will be left with 1 by 2 pi. So let's take all the constant values outside. So we will have j omega divided by 2 pi integration minus infinity to infinity x of omega e raised to j omega t into d omega, right? So this will state as the time differentiation property. So because what we are left with, basically we are left with 1 by 2 pi integration minus infinity to infinity j omega x omega j omega into x of omega and e raised to j omega t into d omega, right? So the Fourier transform is getting multiplied by your j omega value. Now the next property, the convolution property, which is favorite for all the people who are in the working in the image processing domain, because if you are in image processing domain, then you must have worked on it, used the convolution property like thousands of times, right? So what does convolution property states? So it says the convolution operation is a transformed to modulation in the frequency domain. We already know what convolution operation is, right? We discussed it in the previous playlist as well. So, and by the way, if you want to check out those playlists, you will find the link of those playlists in the description below. So the convolution property says the convolution operation is transformed to modulation in the frequency domain. And how does it happens? So let's take the convolution of two signals. Let's say my z of t is equals to x of t convolved with y of t. So when we take the Fourier transform of my signal, so z of omega will be x of omega into y of omega. Now you might have wonder, it's still saying same in it, and how? So let's try to prove it. Let's take Fourier transform of my signal zt. So zt is basically xt in convolution with yt. So when we take Fourier transform, the formula will be minus infinity to infinity xt convolution with yt into e raised to minus j omega t into dt. So now what we will do, we will do the same thing which we did with when we were discussing the properties related to convolution. So we will take xt and yt separately, and we will write, instead of xt we will write x of tau, and instead of yt we will write y of t minus tau, right? Because that is basically formula for convolution, right? That's the formula for convolution. So we can write uh, integration minus infinity to infinity, and then the formula of convolution, which is again integration minus infinity to infinity x of tau y of t minus tau into d tau. That's the formula for convolution, into e raised to minus j omega t into dt, which will be equal to minus infinity to infinity x of tau we will taking outside, and into the bracket we will have minus infinity to infinity y of t minus tau e raised to j omega tau into dt, and then the whole term will be integrated with d tau. So here what we will do, we will take t minus tau is equals to alpha, and then we will take t plus alpha is equals to t, tau plus alpha is equals to t, right? And we will substitute those values in formula of z omega. And when we will take differentiation of this term, so we will get d tau is equals to d alpha, dt is equals to d alpha, right? So the formula will be minus infinity to infinity x of tau, again in the bracket you will be having minus infinity to infinity y of alpha, because we took t minus tau is equals to alpha. So this term, the y of t minus tau, we can represent this term by alpha, and e raised to minus j omega, we what did we do with t? We are putting t is equals to t tau plus alpha, so we will put tau plus alpha here into d alpha into d tau. And when we separate this tau plus alpha term, what we will get? We will get e raised to minus j omega tau into e raised to minus j omega alpha. And after separating that, we can write both of them separately. We can write them as minus infinity to infinity x of tau e raised to minus j omega tau into d tau, and then in again in multiplication, another integral term, integration minus infinity to infinity y of alpha e raised to minus j omega alpha into d alpha. So what both of these both of these integral terms representing, they are representing the Fourier transform for x of t and x of y of t. So we will write x of omega into y of omega, and that's the proof for your convolution. The next one is integration property, which is a little complex than we all see integration as. So let's see what does it has to say. So it says the integration in time will represent smoothing in time domain, and this smoothing in time will correspond to the de-emphasizing the frequency component of my signal. Now how will it de-emphasize the high frequency component of signal? Let's see. So mathematically we represent it by my if you are taking integration of your signal with respect to d tau, so it will be minus infinity to tau, integration of minus infinity to tau x of tau into d tau. The Fourier transform of this signal will be pi into x0 into delta omega plus 1 by j omega into x of omega. Now, by the way, delta omega is your impulse. We know what impulse is, right? Now let's try to prove it. So we will consider convolution of x of t and y u of tau u of t, and we will write the formula for convolution for x of tau into u of tau, which is this. And by the way, remember what is u of t or u of tau? It is unit step signal. So the definition of unit step signal says that u of t minus tau will be equal to 1 for all t, all the tau less or equal to t, right? That's the kind of mathematical definition for unit step signal with t, which is having value t minus tau, right? So it will be 1 for all the values of tau less or equal to t. So basically, if you are taking u of t and if you are taking basically if you are taking u of t, so its value will be 1 for all the t greater than 0, right? So assume that your tau is equals to 0, so u of t will be 1 for all the values of u of t will be 1 for all the values of t greater than 0. So when we take the convolution of this x of t into u of t, what we will have? We will have integration minus infinity to t x of tau into d tau. Now we are taking Fourier transform of this integration. So when we take the Fourier transform of this integration, and we already know what happens with the convolution property, we already stated it a minute ago. So what will happen? We will use this convolution property, and by using that convolution property, we will get the multiplication of x of omega into u of omega, right? Unit step signal will also get the Fourier transform. Then we also state that the Fourier transform of unit step signal u of omega will be equal to pi into del omega plus 1 by j omega. Okay, that is the Fourier transform of your unit step signal. We have not derived it yet, we will derive it soon, but that is the Fourier transform of your unit step signal. So by knowing that this is the Fourier transform of unit step signal, what will happen? It will look like this: x of omega into, this is the Fourier transform for u of omega, so you will substitute u of omega by this term, pi del omega plus 1 by j omega, right? And then you will simply multiply your x of omega in this bracket and you will get this term. And because x of omega into del omega will be equal to x of 0 del omega, so this equation will be represented by this formula as well, right? Now the next property is modulation property. So let's see what this modulation property has to say. It says that modulation in time domain will correspond to the convolution of spectrum in frequency domain. Okay, so whenever you do modulation in time domain, you will get convolution of spectrum in frequency domain. So let's see the mathematical operation. Z of t is nothing but multiplication of x of t into y of t, and when you take the Fourier transform of your z of t, you will get z of omega, which will be equal to 1 by 2 pi x of omega convolution with y of omega. Okay, so here firstly you are taking modulation in the time domain, but in the frequency domain you are getting convolution, right? So how is it happening? Let's try to see it mathematically. Let's take z of t and let's take the Fourier transform of it. So when we take the Fourier transform, the term will look like integration minus infinity to infinity x of t into y of t into e raised to minus j omega t into dt into d omega. And we all know what does the inverse Fourier transform states. We saw it in the earlier part of our lecture. So it says x of t is equals to 1 by 2 pi minus infinity to infinity x of lambda e raised to j lambda t into d lambda. That's the formula for inverse Fourier transform, right? To obtain my time domain signal from frequency domain signal. So when we put this inverse Fourier transform formula in the formula of z omega for x of t, what we will get? We will get a term which will look like this. See, the rest of the things are remaining as it is. You are only substituting the formula for x of t with the help of this inverse Fourier transformation formula for x of t, and the rest of the things are as it is. See, right? So now what we will do, we will take this x of lambda outside in integral. So we will, what we will be left with, we will be left with 1 by 2 pi integration minus infinity to infinity x of lambda, and we will keep rest of the things as it is. So y of t into e raised to uh, this term and this term will get multiplied, so it will become e raised to minus j omega minus lambda into t dt into d lambda. And um, when you take the integration of it, what you will get, so basically when you see this doesn't this look familiar? It is nothing but the one of the properties which we saw earlier, and based on that we were getting y of omega minus lambda. So the final output will be 1 by 2 pi minus infinity to infinity x of lambda y of omega minus lambda into d lambda, and you can represent it because look at this. What is this? This is nothing but the formula of convolution for x of lambda into x of lambda convolution with y of omega minus lambda. So you can write it 1 by 2 pi x of omega in convolution with y of omega, right? The 10th property is duality property. So it can mathematically expressed by, if you are when you take x of t and you take the Fourier transform of it, the output will be 2 pi into x of minus omega. So how does it happen? So let's see. This property has to work with your inverse Fourier transform. So what we will do, we will see inverse Fourier transform situation first. So the formula of inverse Fourier transform is given as here: x of t is equals to 1 by 2 pi minus infinity to infinity x of omega e raised to j omega t into d omega. Now what we will do, we will interchange the t by omega. Okay, we will simply interchange t by omega. So what we will get, so basically we will put this omega and this omega aside, and we will substitute it by t's. So x of and in the output as well. So x of omega will be 1 by 2 pi minus infinity to infinity x of t e raised to j omega t into dt. And then we will interchange the omega by minus omega. So x of minus omega will be 1 by 2 pi minus infinity to infinity x of t e raised to, because we are putting minus omega, we will get minus j omega t into dt, right? So based on that, what you are getting, we will taking this 2 pi on the right hand side, so you are getting 2 pi x into minus omega is equals to minus infinity to infinity x of t e raised to minus j omega t into dt. So this is this x of t minus j omega t into dt. This is the formula for your Fourier transform, right? It is formula for Fourier transform of x of t. So you will get 2 pi minus omega will be equal to the Fourier transform of your x of t, which is x of omega, right? Now the next property is the symmetry property. We also symmetry in the signals as even odd signals. So here it has a similar thing. You can find the even and odd parts from your signal. So let's say x of t is the signal, and remember if we have discussed that every signal can be divided in its even and odd parts. Every signal has even and odd parts of itself. So let's say we have a signal x of t, and the Fourier transform of that signal x of omega will be xr of omega plus j into x1 of omega, right? So what will happen, we'll have some even and odd parts. So the Fourier transform of even part of my signal will be xr of omega, and the Fourier transform of odd part of my signal will be j into x1 of omega. Okay, now how does it happens? So let's try to take the Fourier transform of my signal x of t. So because x of t is a real signal, so let's take x of minus t. So when we take the Fourier transform of x of minus t, we will get x star of omega, and x star of omega will be x r of omega minus j into x1 of omega, right? So you can find the even part and odd part based on the formulas. You know what are the formulas for finding even part and odd part, right? 1 by 2 x of t plus x of minus t, that's the formula for finding even and odd parts. So that's the formula for even part. For odd part, the formula is 1 by 2 x of t minus x of minus t. So you know the value of x of t, you know the value of x of minus t. So now you can find the Fourier transform for uh, both even and odd parts. And when you will find the Fourier transform of even part, you will get xr of omega. And when you will find the Fourier transform of odd part, so at that time you will get jx1 of omega. So you are getting the Fourier transform of even part as xr of omega, and the Fourier transform of odd part is jx1 of omega, and that states this symmetricity property. Now the last property which I wanted to discuss is called Parseval's theorem, or Rayleigh's theorem. So what does this theorem says? It says energy of signal can be obtained by interchanging its energy spectrum. Okay, so this holds some similarity with the energy and power signals, if you remember the formulas for them. So the energy of any signal can be given by this formula. If you remember the classification of signal part, when we discussed about the energy signal, power signal, we discussed this. E is equals to minus infinity to infinity x of t whole square into dt, and its Fourier transform will be 1 by 2 pi minus infinity to infinity x of omega square into d omega. If you are taking f as frequency, so it will be f. Now let's try to prove this Parseval's theorem. So we will take a signal x of t, and we will try to find the energy of that signal. So it will be integration minus infinity to infinity x of t whole square, or x of t square into dt, and by taking x of t square, which means we are basically multiplying x of t with itself. So you can write x of t into dt as well. Now what will be the inverse Fourier transform of my signal x of t? The inverse Fourier transform will be 1 by 2 pi minus infinity to infinity integration minus infinity to infinity x omega e raised to j omega t into d omega. Now when you take the conjugate on both of the side for this inverse Fourier transform formula, you will get x conjugate of t is equals to 1 by 2 pi integration minus infinity to infinity x conjugate omega into e raised to j omega t into d omega t, right? And this x conjugate formula, we can put it in this multiplication formula, because basically we were getting x of t into x conjugate t, right? X of t whole square, when we were taking in the modulus, we were getting x of t into x conjugate of t. So when we put this x conjugate formula in that, what we will get? We will get this term e is equals to minus infinity to infinity x of t 1 by 2 pi, again integration minus infinity to infinity x of x conjugate of omega into e raised to minus j omega t, right, into d omega. So basically we are just putting the value of x conjugate in the formula of e, and when we sum this up, we will be left with this 1 by 2 pi will come out of the integral, and one integral will stay with minus infinity to infinity x star omega, x conjugate of omega, and the remaining term will be minus infinity to infinity integral x of t into e raised to minus j omega t into d omega. So what is this formula? What does this formula stands for? This formula is formula for Fourier transform of x of t, right, which is x of omega. So here you can write 1 by 2 pi integration minus infinity to infinity x conjugate of omega into x of omega into d omega. Now again, what is the formula? What does this formula states? So it is again showing you the formula for 1 by 2 pi minus infinity to infinity integration modulus of x of omega square into d omega, right? And because you know the value of omega is equal to 2 pi f, so when you take the differentiation, the d omega will be 2 pi into df. So you can also write this formula in terms of f as well, right? So energy will be minus infinity to infinity x of f whole square into df. So what did we just prove? We proved that energy signal or energy of any signal can be obtained by interchanging its energy spectrums, right? So you just interchange the energy spectrum and you will get the energy of your signal. So these were the properties, all the properties of my Fourier transform. And moving further, we will try to cover the Fourier transform calculations for periodic signal, and then we will move forward towards the Laplace transform. So we will keep this lecture till here. Thank you very much for listening. The lecture has been a little longer than usual, so apologies if it is inconvenience for some of you, but we will keep this lecture for till here, and I will be seeing you in the next lecture. Until next time, thank you very much for listening and goodbye. Take care of yourselves.